everyone. Good afternoon or good evening, wherever you're joining us from. Thank you so much for tuning in to my talk today. I will be speaking about the secret life of pets. So PET stands for Privacy Enhancing Technologies, and I'll be talking about how you transform data privacy with federated learning and privacy enhancing technologies. Just a raise of hands, or you can type it in the chat. How many of you have already worked with machine learning? So I'm just checking the chat here. Okay, so I'll also give you an introduction of machine learning as well, in case we have some beginners in the audience, but this talk will basically be about privacy preserving machine learning. So before we get started, I wanted to introduce myself. So I am a senior security researcher, and I currently work on AI and machine learning security. So that means how do you attack AI, and also how do you defend AI from being attacked? I have a doctorate in cybersecurity analytics, and my research focus was on AI and machine learning security, and specifically on federated learning as well, which I'll touch on in this talk today. And just as a disclaimer, today I'm speaking on behalf of myself, and I'm not representing any of my employers. So the best way to get in contact with me, if you have any questions after this talk, is to contact me on LinkedIn. So I have my QR code, which goes to my LinkedIn, so go ahead and scan that. So first, we might have some beginners in the audience about machine learning. So just at a high level, machine learning, or AI, just think of it like a very powerful data analytics tool. So in order for machine learning to work, it needs a lot of data. And this data could have sensitive information. Like imagine you're in a hospital. It might have patient records, like not only the patient names, but also ethnicities, health conditions, and all of that information. So when we're using machine learning, we need to ensure that we have data privacy. So what is data privacy? So basically the idea behind data privacy is that we want to protect personal data. So only authorized people should have access to personal data. Personal data could mean health records, age, location, family information, and we want to protect that information because we don't want everyone in the world to know that. And so when we talk about data privacy, a lot of us might be on social media. And so typically when we have a social media account, we can determine whether we opt in or out in terms of making our account private or public, and how much information and when we want to share our personal information with the world. So when we're preserving our data privacy, we're determining when we can actually disclose this private information and how we want that private information to be used. So while in an ideal world, all of us would like to have perfect data privacy, this isn't always the case. And of course, criminals and threat actors try to monetize our private data because they want to make money. So sometimes people will spend a lot of money to get access to someone's private information. And maybe criminals also want to sell their private data so that they can defame their victims. Maybe they want to sell the private data of a celebrity so that they get money for that. Or maybe they even want to monitor people. And if you monitor people, that restricts your freedom, because if you're monitoring someone, you lose your right to be private, and that can also cause you to no longer have freedom when you're living. So of course, data privacy is something very important for us, but criminals will try to take advantage of people and sell this private information. And machine learning is processing all of this private information It has so much data. So in some cases, machine learning can actually be attacked and reveal private information to someone who is not authorized to do so. So for example, maybe a criminal hacks a machine learning system hosted by a bank, and then once they hack the bank, they can access the customer information, maybe the bank account information, maybe access money for different victims. So sometimes machine learning could be attacked and reveal this private information. So typically in machine learning, we have all of our data stored in a database. And in traditional machine learning, all of our data is stored in one database. And now let's say there's a hacker and he has access to the database. Then if your database is hacked, all of your data is compromised. And in traditional machine learning, all the data is stored on a central server. And that makes it easy to access this private data. But there's actually another way that is a privacy preserving version of machine learning. So federated learning is basically a new machine learning technique. So instead of having all of your data stored on a central server, you're actually storing your data in a decentralized manner. So basically, think of a network of mobile phones. So every phone has its own data repository, its own data set. And the data on your phone is not shared with other people. So it's just on your phone, and no one can access your phone except you. So then in federated learning, it's basically a distributed machine learning technique with decentralized devices. So that means mobile phones, for example, and a server. So each client or phone is storing the data and training a machine learning model using its data. So in machine learning, we typically want to train it on data so that it learns patterns from the data. So that's why we need clients to train the machine learning model using their own data. And in traditional machine learning, the server would actually have access to all of this data. But now what's happening is the clients are only providing you an update to the machine learning model. You're not actually getting the data if you're the server. You're just getting an update to a machine learning model. So in this case, the server is averaging all received client updates to combine all of them to create a new machine learning model. So effectively, it's creating a machine learning model using all of these data sets from different phones, but data is not actually shared to the server. So that's why it's more privacy preserving, because in order to access the entire data set used for the machine learning model, you would need to hack each and every phone, which is not feasible. But instead of having to hack each and every phone in a traditionalized machine learning model, you would just need to hack one thing and you get access to all the data. So that's why federated learning is a more privacy preserving framework for machine learning. And federated learning has been shown to be enhanced using PETs or privacy enhancing technologies. And this is a growing research area that a lot of global companies are using, like IBM, Google, and Microsoft. So privacy enhancing technologies are basically a set of tools and techniques that are designed to enhance the privacy and security of data and of online communications. So some of the privacy enhancing technologies we'll talk about today include secure multi-party computation, homomorphic encryption, and differential privacy. So the first PET I want to talk about is this idea of secure multi-party computation. So in secure multi-party computation, participants are communicating with each other, but no participant learns anything about the other people. So for example, if you have a group of friends, you all work together to complete a task, but you don't actually share any information with each other. So think of it like I have one task I'm working on, and together we're working to create a sculpture. And I'm only doing one task, and you might be doing another task. And so we're each going to do our own assigned tasks, but we're not sharing our personal information or our personal data. We're just giving you the information you need to know so that you can continue creating the sculpture. And so in secure multi-party computation, there's this idea of secret sharing. So basically, we're going to say our secret is maybe the design for the entire sculpture. And so we're going to divide the design for the entire sculpture. So I only know, for example, one part of the sculpture or one part of the painting. And because of that, we're dividing the secret so no one can see the full picture. And also there's this idea of homomorphic encryption, which we'll talk about later, which also preserves privacy. So in federated learning, they actually use secure multi-party computation for secure communication, computation, and privacy preservation. And actually, JP Morgan created a proposal using this PET in federated learning. And if you're interested, the paper is over here, but this is something that the industry is looking at right now. And now that brings me to the second PET we'll go over today. So homomorphic encryption. Homomorphic encryption, you might have heard about it, but basically the idea is that instead of working with unencrypted data, all of the data that we're working with will be encrypted. So we're performing any of our calculations only on encrypted data. So in this case, let's just say we have a client, and the client is sending updates to the server. Like I mentioned in federated learning, it's sending updates to a server. But instead of sending the updates in the clear, so for those of you who work in cybersecurity, you might know about Wireshark and how you could eavesdrop on the traffic that you observe when you're listening in to certain traffic on the network. So when you encrypt your update, basically, even if you were to use something like Wireshark, you won't be able to actually determine what's in this update. It will just look like gibberish for you. So when the phone tells the server that I have this model update, it's all encrypted. So the server can only perform these computations using the encrypted model update. It can't actually see what the model update is. And this is something that IBM is using in their proposed approach for federated learning, and they advocate for using homomorphic encryption. And finally, the last PET that we'll talk about today is this idea of differential privacy. So how many of you have actually heard of differential privacy? Okay, so differential privacy is something you might have heard of if you studied cryptography. But basically, the main idea behind differential privacy is you're basically masking the data used by the model. So you're trying to mask all of this data so that even if someone was to hack a phone and get access to your data, it's all masked, it's all hidden. There's some kind of noise. So even if I were to hack a phone, I couldn't actually see the raw data. I see something that's hidden and obscured. So that's an example of using differential privacy. In differential privacy, they typically add noise to the data inputs and to the models. So basically, for example, in machine learning, if I have a machine learning model and it tells me this image is a mask, and maybe let's just say we have another image of a dog, and it says this image is a dog. And so it's just an image recognition tool. And what this differential privacy approach can do is it can basically tell you this mask, it's actually a dog, or a dog is actually a mask. So you're basically adding noise to the model and to the data inputs. So if someone were to ask the machine learning model, what is this object? It would give you an incorrect answer. So that's meant to fool the attacker. And this is actually used in the medical setting, in hospitals and in healthcare to preserve the privacy of their data. And there has been some research proposing that you use differential privacy in federated learning, and they are basically advocating for this idea of adding noise to less important features to preserve accuracy. So for example, let's say I have a image recognition machine learning tool, and maybe there's a feature or an aspect of the image that is not as important. So maybe if I just add maybe different color over here, maybe that will add some noise to the data, but it doesn't really cause the performance of the model to change, but it does cause someone to get confused if I change the color here, for example. So this is actually very important, and this is something that we are actively researching now, and it can be applied to so many different fields in the industry. So these are just 3 examples, but it could be applied to anything that's using machine learning, which is pretty much every industry today. So it can be used in telecommunications. So in telecommunications, the main idea is it's used for creating cell phone connections, right? So whenever we make a call to someone or we text someone, it's using telecommunications. And in telecommunications, there's this idea of communication service providers, or CSPs. And for 5G and for 6G, which are basically the next generations that you'll see on your cell phones soon. So communication service providers are basically using federated learning to analyze consumer data while ensuring privacy. So how this works is every time we're in a city, so let's say all of us are sitting in San Francisco right now, and we're all making phone calls in San Francisco. Maybe in 5G, what they're doing is they're getting all the data from all of our phones in San Francisco, and they're analyzing all of our data to say, okay, we see this concentration of people in San Francisco, so we know we need to allocate more resources to San Francisco, but they also add privacy preserving mechanisms, so they can't actually see any of our identifying characteristics. They just know the information they need to know in order to enhance the efficiency and to reduce the latency. So basically, when we make calls or we text someone, we want our phone calls to go through really quickly, and we want our messages to be delivered really quickly. So in order to do this, telecommunications is actually using federated learning to not only preserve privacy, but to also increase efficiency. And it's also being used in healthcare. So they actually use this in healthcare to collaborate among different hospitals. So in COVID-19, when the pandemic hit, and all of us were trying to figure out what's happening, and a lot of hospitals were researching COVID-19 and how it works. So as you might imagine, hospitals don't want to actually share their data with other hospitals or with other parties. But what they could use is federated learning. And federated learning, what it did was it helps you combine records from one hospital and another hospital so they can collaborate on machine learning. So they're not actually sharing the data itself, but they are collaborating on a machine learning model so that they all collaborate and derive insights about how COVID-19 is working, while also preserving the privacy for their patients. And finally, it can also be used for IoT devices to train models on data from different devices. So federated learning has been used with IoT devices to also preserve privacy. And now you might find this very interesting, but how do you actually apply it, right? So in federated learning is something people are using today in the industry. And there are so many different tools and frameworks that engineers in your organization or data scientists could use to implement federated learning. So here are just a few of them. So there's PySwift, which is a Python library, FATE, which is also available in Python, TFF or TensorFlow, which is a popular Python framework for machine learning. And finally, there's Flower. So Flower is a framework that you could use in Python, but you can also use it in other languages as well. And it provides you a nice way to implement federated learning without having to go through the back-end details of it. So all of these tools are open source, and you can program your own federated learning algorithms using these tools. You could import them, for example, in Python or in Go or in Java if you're using Flower. So there are many ways to apply this technology. So that concludes my presentation. I'm now opening it up for questions for the last 5 minutes. If you have any questions, feel free to contact me on LinkedIn or on X. Thank you so much.